We certainly can. Which one you got? Cars stop on a dime. Calculate the acceleration a 1,400 kilogram car, if it can stop from 35 kilometers per hour on a dime, which is a diameter of 1.7 centimeters. How many G's is that? What force is felt by the 68 kilogram occupant of the car? Okay. Morning, Tony. Let's see. First, let's get 35 kilometers per hour into meters per second. "35 kilometers per hour times 1,000 meters for every 1 kilometer times 1 hour for every 3,600 seconds. And that gives us, everybody get out your calculators. .72 meters per second. Now let's see. We've got, let's look at the numbers we're given. We're given 1,400 kilograms. Mass of the car. We're given 35 kilometers per hour. It's the velocity, the speed of the car. And we're given the diameter of a dime is 1.7 centimeters. That's our stopping distance. And in all of these cases, we've got two significant digits. So let's leave that at 9.7 meters per second. Oh, and we've got a 68 kilogram occupant of the car. Now, first thing we need to know is how much acceleration would it take to stop the car in 1.7 centimeters, which is 0.017 meters. Well, go back to our handy-dandy kinematic equations, and we've got v sub x squared is equal to v naught sub x squared plus 2 a sub x delta x, x minus x sub naught. Did I get that right? Okay, what's our final velocity we're shooting for? 0. So we have 0 meters squared per second squared, because it's 0 squared, will be equal to 9.7 squared meters squared per second squared, plus 2 times A, that's what we're looking for, times 0.017 meters. If we subtract this from both sides, we get minus 2ax times 0.017 meters is equal to 9.7 squared, which is 94.5, so we'll call it 95. Meters squared per second squared. We divide both sides by 2, and we get ax times 0.017 meters is equal to 40. That's still a negative because we divided by 2, not negative 2. 47.3, so 47 meters squared per second squared, which that we can divide by 0.017 to give us an acceleration of 2,780 meters per second squared. So what happened to the square meters? Divided by meters. That left meters per second squared, so our units do work out. And since we're only limited to two significant digits, we make that 2,800 meters per second squared. That's how fast, that's the acceleration that would be necessary to stop a 35 kilometer per hour car on a literal dime. Now let me find the question again since I absent-mindedly closed the book. That's the first part, right there. That's A. You'll notice the negative sign means that it would have to be in the opposite of the direction of motion. Okay, what's the next question? How many G's is that? Well, 1 G is what? How many meters per second squared? 9.8. So if we divide that 2,800 by 9.8 meters per second squared, that gives us 285.7, which to 2 digits would be 290 G's. You'll notice that G's are actually unitless, right? Or we could call the G the unit. Say it's 9.8 meters per second squared per G. All right, now, final questions. What would the force be felt by a 68 kilogram occupant of the car? What is Newton's second law of motion? Force equals mass times acceleration. 68 kilograms times 2,800 meters per second squared equals who's got an answer? 190,400, or to two significant digits, 190,000 newtons. How big is that? How much force is that actually? Because face it, we don't think in terms of newtons. We think in terms of pounds. What's 1 newton is what, 4.5 pounds, roughly? 1 pound is 4.5 newtons? Something like that. Yeah. That's over 40,000 pounds, 42,000 pounds. So, could to answer the albeit rhetorical initial question, could a car literally stop on a dime? It would kill anyone in it if it did. If you were wearing your seatbelt, then you would be cut into 3 pieces, and those 3 pieces would be squashed flat. If you had an airbag go off in front of you, it would mean that it would hurt for like a half a second longer before you died. No, albeit rhetorical, no, you cannot literally stop on a dime. But it's still fun to drive sports cars that make you feel like you can. Did anyone else have any homework questions? No? All right. Y'all realize that when I go to grading your papers, it's only work for me whenever you get the wrong answer. When you get the right answers, it's easy. It's like check, 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 check. That one's good. Check, 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 check. That one's good. But when y'all get the wrong answers, that's when I have to start working and figuring out, well, no, wait a minute. What did they write? Wait, is that a 4 or a 9? What were they doing? What? So, if y'all don't have any questions from the homework, then I can only assume I'm going to have an easy time grading these. All right. Newton's first law of motion. Law of inertia. And the normal statement of the law of inertia is the colloquially popular statement. Object in motion will stay in motion. Object at rest will stay at rest. More generally, it's a statement that all matter will resist acceleration. Okay. What's the second law of motion? Very close. Try again. Get it correct. The sum of all the forces. And it's a vector sum. The vector sum of all the forces acting upon a body will equal the mass of that body times its acceleration. This is a corollary to the first law. First law is a statement that all matter will resist acceleration. Second law is a statement of the force required to overcome that resistance. Now, it's the third law of motion. Every action has an equal and opposite reaction. That's the colloquial statement of that. Chapter, there we go. What it means is that if one object or body or mass exerts a force on another object or body or mass, then the other body or mass exerts an equal and opposite force on the initial body and mass. You push on something, it pushes back on you with an equal and opposite force. When you push to open a door, you feel the weight of that door. What you are actually feeling is the reactionary force that that door is exerting on you. You do not feel the force that you apply to the door. What you feel is the force the door applies to you. When your feet hurt, because you've been on them all day, walking, you do not feel the force of your feet pressing down on the ground. What you feel is the force of the ground pushing back up against your feet. In other words, you only feel the forces that are applied to you. You do not feel the forces that you apply to another body or object or mass. That body, object, or mass feels, or in whatever way it does, experiences that force. So, what force actually causes your car to move when you step on the gas pedal? Say again? There's a lot of things going on. The tire pushing against the ground, when the wheel turns, the tire pushes against the ground. And hopefully the ground pushes back against the tire. If it does, then that force of the ground pushing back on your tire will cause your tire to roll forward. What happens if that ground doesn't exert a force back on your car, on your tire? Your tire spins and you don't go anywhere. If you're driving on ice, well, if you're driving on ice, you're not driving, you're riding. All right? How many of you have actually tried to walk on ice before? Ever? It's not very easy to do, is it? Kind of, what do you got, that little duck waddle thing? You got to keep your center of mass directly over your feet the whole time, because you're not going to take a normal step, because the ice isn't going to push back on your foot. That means your foot's just going to slide right out. You're not moving yourself forward, you're moving your foot behind your center of mass, which means you fall over. We talked about this. Let's revisit it again, just to make sure everyone's clear on this. Well, I think I use the example of pushing a box. In the book, they use the example of one of Michelangelo's assistants dragging a sled with a huge block of marble on it. Well, he grabs the lanyard or the rein or the rope or whatever's tied to the handle of the sled, and he pulls on it. He grabs the handle of the sled and he pulls on it. Well, when he pulls on it, he exerts a force on the sled. What happens to the sled? the sled exerts an equal and opposite force on him. So how does if the forces exactly cancel each other out, how does the sled ever start to move? This goes back to the second law of motion. It's not the one force that matters, it's the sum of all the forces. So if that were the only force involved, then of course there would be no motion, because think of it this way. It's a good way to think of it. Imagine there's a box here, and I grab the handle, or a sled with a big block of marble on it. I grab the handle, and then I put my feet on the runners of the sled, and I pull on that handle as hard as I can. How fast is how much acceleration am I going to impart on that? How much am I going to accelerate that sled with the big marble on? None. Because every ounce of force I'm exerting on that box. And it's doing what? Until and unless the handle breaks, it's just exerting an equal and opposite force on me. So no matter how hard I pull, I'm not moving and the box isn't moving. We're both going to sit there motionless. But if I take my feet off of the runners and I put them on the ground and now I pull, I'm exerting a force on the box. My feet are exerting a force on the ground. The ground is exerting a force on me. Now, the question is, what are the sums of those forces? And if I can accelerate myself, if I can force my body, if I can make the sum of those forces enough that I start to move, as long as I do not let go of the box or the sled, it's going to start moving with me. So, we talked about, I think I even mentioned the idea of the normal force. Who can tell me what the normal? Not raising your hand, right? Okay. I was going to say, well, now that's on the ball when you're raising your hand to answer the question before I even get it out. Who can tell me what's the normal force? And no, it's not a force that's not weird. Say again? Not really. Gravity definitely produces normal force. And a lot of people equate the normal force with the force of gravity, because that's generally the examples we use when we think about it. What does the word normal in this context actually mean? Because there are different meanings of the word normal. If this were my stats class, then normal means a symmetrically distributed population about an arithmetic mean. Or maybe it means plus or minus 3 standard deviations around the arithmetic. But this isn't statistics. This is physics. Mathematically, in context of physics, what does normal mean? Anybody? No, it means perpendicular. It really doesn't have any, it's almost completely disconnected from the other meaning of the word. But when you see the word normal in this context, that's all it means, is perpendicular. Okay? Straight up, upright. Okay? And that should give you a kind of a hint as to how the same word that means perpendicular, upright, normal, also came to mean within the standard deviation of a population distribution. The normal force is perpendicular to the point of contact, to the force that is reacting to, the reactionary force is always, according to the third law of motion, it's always equal and opposite. So in this case, set the cup on the table. The mass of the cup times the acceleration due to gravity is the force that the cup exerts on the table. The table exerts the normal force, an equal and opposite force to the force of gravity on the cup. And that's why people tend to think of it as the opposite of the force of gravity. But it isn't always. In the case of the guy pulling the sled with the big boulder on it, or the big block of marble, when he's pulling at an angle. The normal force to his pull is in the opposite direction. So if he's pulling at 30 degrees above the horizontal, the normal force will be minus in the opposite direction and 30 degrees below the horizontal. The magnitude of the normal force is also not always equal to the mass times gravity, to the force due to gravity. Let's work through this example here. I'm going to try to write it. Let's talk about it and look at it on the thing. I've got this book on the table here. Call it a box. If you want to follow along, I'm on page 85. The weight of this book on the table is the force due to gravity that the book applies to the table. The table applies the normal force in the equal and opposite direction. And as long as the book is the only weight being applied, the normal force is equal to the weight of the book. But instead of straight down, it's now straight up. What happens if I press on the book and I push down? I'm now adding an additional force to the weight of the force due to gravity. So now, how much is the normal force? It's the sum of it's equal and opposite to the sum of the force of the book due to gravity and the force that I'm applying in addition to that. Here's the table. Here's the box. This is the mass of the box times gravity. This is the normal force that the table is applying to the box. I come and I apply an additional force of 5 newtons. Let's say the mass of the box is, 10 kilograms, so that would be 98 newtons. Now, before I press on it, the normal force is 98 newtons in the opposite direction. When I press down with 5 additional newtons of force, now what's the normal force? I'm saying down is negative. That's the sum of the forces. What's the acceleration? 0. So all of these forces equal 0. So what's the formal the formal Norse? What's the normal force equal to? Add 98 to both sides and 5 to both sides, and you get before I'm pushing down on the box, the normal force is 98 newtons. Once I push down on the box, the normal force is 103 newtons. this is one of those things where because it's reactionary, and we're gonna hit this again when we talk about friction. Because the force is reactionary, it will never exceed the force that causes it. Okay? How much force could this table exert? I don't know. I'd have to press on it hard enough to find out when does it crack. Okay? Now, if it cracks, if you exceed the normal force that it's capable of producing, then you will get acceleration. Okay? It will move. It will break and you'll fall to the floor. But as long as you do not exceed its maximum limit that it's capable of producing, it will only produce as much as needed to counter what's causing it. Am I explaining this well? Because the fact that it's a reaction, it's not an action, it's a reaction. Its quantity, its magnitude is dependent upon the action. I hope I didn't just confuse y'all. What if, instead of pushing down with 5 newtons of force, what if I pulled up on it with 5 newtons of force? One moment. Say what you said again. It would. It might, but it may or may not. That's a good point, because that's exactly where we're going. So hold that thought. Now, I'm sorry, what did you say? What's going to happen is the sum of the forces is still going to be the net force. So we now have plus 5 newtons plus the normal force minus 98 newtons of the force due to gravity. And does the box move or not? Well, in this case, let's see, what is the normal force? (98 newtons equals 5 newtons plus normal force. So the normal force now is 93 newtons. Box does not move. The acceleration is still 0. But if you lift hard enough, if you lift with more force than the weight of the box, then this normal force would become negative. Only it's a reactionary force. It can't be negative, which means any excess force that you produce would equal the mass times acceleration, and the box would at that point lift. Let's go through that example. As at this time, let's say we lift on the box with 98 newtons. Let's say we lift on the box with 100 newtons of force. Now we've got the box with 10 kilograms, so it's 98 newtons going down. The normal force is pushing up, and we are lifting on the box with 100 newtons. Now what are the sum of the forces? So start by solving for the normal force. Well, if we assume that that there is a normal force, then that means the box is still resting on the table, motionless. So we add 98 to both sides. Now we subtract 100. And we get a negative normal force, which cannot happen. That means the normal force is now 0. And what's left over is the 2 extra newtons of force pushing up. That means our sum, basically the sum of our forces now, this is 0. So now the sum of our forces is equal to 100 minus 98 equals plus 2 newtons. Now, how fast does that box move when we lift it? How much acceleration does it experience when we lift it off the table? That's right. Force equals mass times acceleration. 2 newtons equals 10 kilograms times the acceleration. 2 divided by 10 is 0.2. 0.2 meters per second squared. Look at me doing arithmetic in my head. Say again? No, seriously. Did I miss something? Kilograms, meters per second squared. Yeah. 0.2 meters per second squared. That's how much acceleration the box will experience when we lift it. This is another one. This one is kind of, I think this one actually relates to one of your homework problems. So let's work through this example. Because it may not be as intuitively obvious as you would think. We're going to look at the weight of a person on an, you notice I said person, not woman. Don't ever talk about a woman's weight, period, ever. If they ask, run, it's a trap. You got a person standing on a scale in an elevator. You're going to laugh at my drawings on your own time. How much does this person weigh? Say that it's a 65 kilogram occupant. Now the elevator accelerates briefly downward at 0.20 Gs. How much is that in meters per second squared? .96. Okay. I just want to make sure y'all understand what that means when I say 0.2 G. 20% of the acceleration due to gravity. And of course, it's only for a moment that this happens. It only accelerates for a moment until it reaches its constant velocity, at which point it no longer accelerates, it moves at a constant velocity. So let's talk about 2 different time intervals. Let's talk about that brief moment when it first accelerates downward, and then once it's accelerated, it stabilizes at a constant velocity. Okay, let's start with what are the sum of first of all, the weight that is read on that scale. How much weight does the scale show? Yeah, 65 kilograms because the force exerted on it is 65 kilograms times G. And the normal force of the elevator pushing up on it is how much? 65 G. 65 kilograms times G. Right? And at that point, it measures 65 kilograms. So, the sum of the forces are the normal force minus mass times gravity. Am I writing that correctly? Yeah. And that would equal 0 as long as the elevator is not accelerating. Okay? As long as this frame of reference is motionless, is not motionless, but is at constant velocity, not being accelerated, then it is an inertial frame, and the sum of these forces will equal 0. At that point, it reads 65 kilograms. What happens when the frame of reference, the elevator, accelerates downward slightly at 0.2 G? Say again? It gets lighter. But this is no longer equal to 0. It's now equal to mass times 0.2 G. Mass times acceleration. Yeah, I did write this backwards. That's okay. If we're now solving for the normal force, which is what the scale reads, it's mass times 0.2 G plus mass times G. And I did get a sign backwards somewhere. Yeah, they're saying in the book that it's reading mass times gravity minus the normal force is what the scale reads. Think that through. This is kind of counterintuitive. It's certainly not necessarily intuitively obvious. Why would they write that backwards like that? They're saying, they're saying this is what the scale reads. So when they solve it, they write mass times gravity minus force normal minus mass times 0.2g equals 0, and then add the force normal to both sides, and they're left with mass times gravity minus mass times 0.2g equals the normal force. So they factor out the mass, g minus 0.2g equals mass times 0.8g equals the normal force, and that the person reads during that momentary acceleration of the elevator that they read 80% of their normal weight. Mass times gravity times 0.8, where mass times gravity is their normal weight. Yeah, and they say right here that the direction of acceleration is downward, so they choose the positive direction as down. Yeah, okay, fine. What happens once the acceleration is over and the elevator is now moving at a constant velocity? At that point, it's just an inertial reference frame, and the scale would read the normal weight. Now, how many of you thought you were finished with vectors, adding vectors, converting vectors? Yeah. Well, we're going to be doing more vectors next week. Yeah, look, y'all can read the problem here in the book, and I just don't like the way they suddenly decided now we're gonna make everything, now instead of acceleration down being negative, we're gonna make down positive and stuff. I don't see why they did it. It simplified the algebra. But to me, part of the beauty of the math is that you shouldn't have to manipulate it like that to get the same result. But I guess there are times when simplifying it is worthwhile. Any more questions? Anybody want nothing? Who's got their homework ready to turn in? No? Okay, just real quick, show of hands. Who has actually started their homework? Okay, well that might tell me why there's no questions about the homework yet. Yeah. Well, I'll sit there for a minute while I go and look, see if there are any that I think are going to give you particular difficulties. All right, well, y'all have a good weekend, and I'll look for you to turn in all your completed homework on Monday.